Okay, welcome back everyone. So we recap quickly what we saw in the last lecture about gradient descent. Remember, gradient descent is going to choose the steepest descent direction immediately, which may sound like a good idea. And with this direction is opposite the gradient. All right, so if we define the gradient in this way, so we call G gradient, we, you know, the derivative matrix of f, first derivatives at point x at the kth iteration, our descent direction dk, so the next step is going to be in direction of negative the gradient, and we normalize it by the gradient's absolute size. Okay, so this is how you derive a gradient descent direction. And one can show, as we mentioned, and you can look up the proof in this great book, that minimizing the step size after you chose this direction, minimizing with respect to alpha, is going to result in a jagged path for the solver. So the solver is going to choose orthogonal directions. Each step is going to be orthogonal to the previous one, depending on the shape of the function where you are right now. And this may spell some trouble. Okay, so let's try and illustrate that with these very cool graphs first proposed by Patrick Kofo-Mogensen, which I slightly adapted for this course. So this one shows you the solver path of gradient descent starting from the yellow dot. Okay, you know these are the contours, and so let's see how this is going to go. So we start at iteration 1. Iteration 2 already makes a big step all the way straight up the hill in the steepest direction. You can see it goes right across the contours, improving a lot. It overshoots, it goes back, and then it starts to make really small steps. You can barely see those. Okay, you can see my slider is moving, but you can see the dot is not moving at all. So let me go forward a bunch more. So you see he lost a lot of time here doing very small steps. So what's going on? Let's see. Let's zoom in into a region where we can see that better. And let's show the step size and along this valley, the movements this thing is making. Okay, let's see. Okay, so you can see the first step size was this big step across the hill, the first step number 1 that we made, very big step. Okay, so that was kind of good. Then we go on, and CC goes backwards. It zigzags along this valley where each step is kind of an orthogonal direction. Okay, you can see how this is going. So very small steps. You can see step size is extremely small down here. Okay, so conjugate gradient was an improvement on this. So it basically avoids exactly this problem, this jagged path, by choosing a different method. So it minimizes a quadratic form of f to derive the new descent, the new direction. And okay, so let's just quickly see how that's going to look. Let's do another little illustration on this. So same function is always the Rosenbrock function, as you know. So we go up again, quite steep steps. Then it's going to turn around and go down the valley without those many zigzags. So it's doing much better already. Okay, so that's good. And so after a couple of iterations, we'll reach the optimum, 45. Okay, so let's compare that with second order methods now. You remember we derived Newton's method as a second order Taylor approximation. So this is in the univariate case. So here we derived the new candidate xk plus 1 as xk minus this Newton step formula here. Similarly, in the multivariate case, you just use gradients and Hessians now instead of first and second derivative. And so we talked about the computational cost in computing the Hessian matrix and approximations to that. Okay, but what I really want to do, I want to show you a little. This is where my notebook tanked the other day. Let's see if I can do better now. So I want to compare those two. Let me just quickly regenerate this plot. It's going to look a bit like that. Okay, so we have Newton versus gradient descent. They both start at the yellow dot. Let's go. First step, you can see gradient descent tries to go along so this is conjugate gradient descent, I should say. Or is it gradient descent? I don't actually know. No, it's gradient descent. Okay, well. So you can see that it tries to go up perpendicular to the contours, as steep as possible. That's what gradient descent does. It chooses opposite the gradient. Newton uses Hessian and gradient information and chooses a different direction. So it goes all the way up and right into the middle of this valley. Turns around, you can see gradient descent already made a lot of way ahead and seems to be doing really well, but then zoom, and you can see that Newton just totally kills it, while gradient descent is still zigzagging around in the bottom of this valley. Okay, so a really impressive display of how fast Newton, the Newton algorithm converges here. So that's obviously whenever you can deploy the Newton algorithm, you really should do that because it's just so fast. We could also see that then if we time these operations and see what this gives, I'll let that to your own leisure. I'll leave it here. I'll see you on Friday.